Okay, I think we can start now. Thank you everybody for joining the sixth session in the Chandra Data Science workshop that we've been putting together for you all here all week. I remind you all that we are meeting again next week, the same 3 days of the week, a slightly earlier start time, and I'll be sending out the information for that in the future. Today's session is a very interesting session. We have a lot of different talks, different subjects again, and I'd like to start by introducing our first speaker, Dan Wilkins from Stanford University. Dan Wilkins is going to speak to us about the statistical approach to measuring X-ray reverberation in gravitationally lensed quasars.
Great. Thank you, Rodolfo, and thank you everyone for joining us. It's a great pleasure to be joining you, at least virtually, to tell you today about how we can extend the X-ray reverberation studies we've been doing of the environments around supermassive black holes, using statistical approaches to extend the reach of these methods to a broader sample of black holes. And in particular, today, I'm going to tell you about how we can start to apply this to gravitationally lensed quasars that we can observe with Chandra. So an outline of my talk, I'm going to start by giving a very brief overview of X-ray reverberation mapping of the inner accretion flows around black holes. And then I'm going to introduce this statistical framework that's based on Gaussian processes. And I'm going to talk about how we can apply that to two particular use cases. The first one is measuring reverberation around higher mass black holes in radio galaxies. And the second use case is applying this sort of framework to Chandra observations of those gravitationally lensed quasars to try and measure X-ray reverberation beyond just the nearby Seyferts. So X-ray reverberation is a tool that's been emerging over the past few years to map the inner regions around black holes. The cartoon picture we have is this accretion disk of material spiraling into the black hole, and then a corona of high energy particles that's formed just outside the black hole. This corona is the source of the X-ray continuum that we see, and this is the primary source of the radiation that we're measuring with X-ray telescopes. Now, some fraction of this X-ray continuum is going to shine down onto the accretion disk, and that means we're going to be able to see not just the direct continuum emission from the corona, but also the reflection of this continuum as it's reprocessed by the accretion disk. In particular, this reprocessing produces emission lines. The ion K alpha line at 6.4 keV in the rest frame is a prominent X-ray line that we see from the inner parts of the accretion disk. But these lines from the disk are broadened by Doppler shifts and gravitational redshifts around the black hole, which gives them this characteristic shape with a blue shifted peak, and then this extended redshifted wing of emission coming from the inner disk close to the black hole. Now, the continuum from the corona is highly variable, and this means that the reflection component and the emission lines will vary in response to the changes in the continuum luminosity. However, there'll be a time delay between the change in the continuum luminosity and in the line emission that corresponds to the light travel time from the corona down to the disk. And we can measure this reverberation time lag. This spectrum shows the response times of the different X-ray energy bands measured by XMM Newton in response to changes in the continuum in a nearby Seyfert galaxy. The band most strongly dominated by the continuum emission responds to the change first, so that response is seen at the earliest time. And then the reflection component at low energies and also the ion K line respond later. And we can see that characteristic wing on the ion K line. There's a shorter time lag for the redshifted wing of the line because that's coming from the inner disk closer to the corona. Now, the key to X-ray spectral timing in mapping the extreme environment just outside the black hole is that the energy shifts of the photons correspond to the positions they were emitted on the accretion disk. So there's a different gravitational redshift and a different Doppler shift from each part of the disk. And then the time delay tells us the distance between each part of the disk and the corona that is illuminating in it. So by combining the spectral and the timing information, we'll eventually be able to reconstruct a map of the inner accretion flow and the structure of the corona. Now, typically, these X-ray reverberation measurements are carried out using Fourier transforms of the light curves. For example, if we want to measure the time lag between energy bands in the spectrum that correspond to the continuum and to the reflection in, say, the soft band or in the INK band, we Fourier transform those two light curves in those two energy bands. And then from those Fourier transforms, we form something that's called a cross spectrum. And then this cross spectrum gives us the time lag as a function of Fourier frequency. These Fourier frequencies are the slow and fast components of the variability that make up the light curve we see. So we get a different time lag in those different timescale variability processes. And then the reverberation lag we measure by convention here is the negative point. It's this point here with the longest time lag. But this method requires high signal to noise. If we have low signal to noise, we can get a lot of scatter in this lag as a function of frequency, and it makes it difficult to interpret. And the longest time lag we can measure is actually limited by the longest continuous time segment we have in our light curves. This means in observations using, for example, XMM Newton, we're typically limited to measuring the light crossing times for event horizons of black holes 10 to the 6 up to a few 10 to the 7 solar masses, because the length of the orbit of the spacecraft limits the longest light curve segment we're able to get. Now, this is a problem if we want to extend reverberation studies to radio galaxies, which are typically thought to harbor black holes an order of magnitude or so larger in mass. And mapping the inner accretion flows and corona in radio galaxies is therefore a challenge using this method, but it can give us important clues if we can measure this reverberation about the structure of the corona and how the corona is related to the launching site of the jet. So there's potentially important insight we can get there. So I'm going to talk about two different but closely related statistical frameworks to overcome these limitations. And those were presented in their application to X-ray data in these two papers, one that I published in 2019, and then another paper published by Abdu Zogpi et al. In 2013. So both of these methods are based on a Gaussian process framework. And in this Gaussian process framework, we express the light curve we have, so that's the count rate in successive time bins, as a data vector. So this vector is essentially just the count rate in the time bins that we've measured. They don't have to be evenly spaced time bins, so long as we know the time of each of those bins. So if we've got n bins in our light curve, we have n elements in this vector. And we assume in a Gaussian process that this vector is a draw from an n-dimensional Gaussian distribution. And by making this assumption, we can define a likelihood function, the probability of obtaining the light curve that we did, given some model description of the underlying variability process. This is similar to fitting Karma models to measure the power spectra of light curves, and it's actually based on the method of Bond et al. That they use to measure the power spectrum of the CMB. Now, light curves aren't just sets of random numbers. They're typically red noise processes that have some memory between successive time bins. So how can just a random draw from a Gaussian produce this realistic red noise light curve? The answer is in the model that we put into the Gaussian, expressed through this covariance matrix, sigma here. The covariance matrix encodes the autocorrelation between pairs of time bins that you can see in this matrix here. So essentially, these are the covariances between the pairs of time bins. But we can write down a simple analytic form for each of these covariances, and we call that analytic expression the kernel function. And one application of Gaussian processes in practice is to fill in the gaps between those continuous segments we have in our observations. So in practice, we might have data points here, 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 and here, shown in black on this plot. But then we want to fill in the gaps between those. To do that, we build the covariance matrix from this simple analytic function that has a number of free parameters that are called hyperparameters. And then we fit these hyperparameters to the observed data points. This means our Gaussian process is essentially learning about the variability that's in the light curve. Once we've trained the Gaussian process by fitting these parameters, we can draw samples from this n-dimensional Gaussian. Technically, we actually draw it from the joint distribution, that's the Gaussian in the time bins we want and in the time bins that we have the data for. And this produces just one prediction of what the missing data points can be. So we can see that as the purple line here. But then we can draw many, many samples from this Gaussian, average over them, and this produces these predicted regions for the missing data. And now with each of these samples, we can treat them like continuous light curves. So we can apply the conventional Fourier transform methods to them. So essentially, we can take one sample of the light curves, we can apply the Fourier transform and measure the time lags. And then we can do this again and again and again with different samples. And this eventually gives us the posterior distribution of the time lag. And this has enabled us to measure X-ray reverberation for the first time in a radio galaxy, in particular 3C120. We can see if we look at the average response times, the time lags between the different energy bands. We see the early response where the continuum dominates, and then we see that characteristic shape of the I and K line time lags, the redshifted wing responding early, and then the core of the line further out. But what about X-ray reverberation in some of the most extreme accreting black holes in our universe? In particular here, I'm talking about the quasars. If we can perform reverberation mapping of the inner regions around the event horizons in a quasar, we can extend our knowledge of accretion to the rapidly growing black holes at high redshifts. And this is very important. The nearby Seyfert galaxies probably aren't black holes that are growing rapidly, and they're not black holes that are really responsible for the AGN feedback that's governing the growth of their host galaxies. But if we can observe the accretion process, the corona and the inner disk, close into a rapidly growing quasar, we can learn and actually see the processes that are likely driving the AGN feedback. But in order to be able to perform this reverberation mapping at all, we need to be able to measure that time lag. So before we can get that lag versus energy spectrum, and before we can combine the energy shifts with the timing data, we need to know if we can even measure this time delay at all in a quasar. However, we get a unique opportunity to study quasars in detail when they're magnified by gravitational lensing. And Chandra is able to resolve the multiple lensed images in many of these systems. Now, just like their lower redshift counterparts, lensed quasars show X-ray emission from a corona and the reflection from the accretion disk in the form of that broad I and K line. For example, this is the Chandra spectrum of the Einstein cross, also known as Q2237 plus 0305, and it's a lensed quasar at a redshift of 1.7. Now, this spectrum was first presented by Mark Reynolds et al. In 2014, and similar studies of lensed quasars were done by Rubens Rees and by Dom Walton, and they show that you can model the spectrum in these lensed quasars with the continuum and that broad I and K line. However, now the I and K line has been redshifted to around 2 keV. And this is ideal for Chandra's effective area. Chandra's not so good at measuring 6 keV ion lines, but if we can shift that line down to 2 keV, it's much more amenable to the effective area curve of Chandra. And using Chandra, we can separate out the emission from the different lensed images. But the problem here is we don't only potentially have a very massive black hole with potentially a very long time lag, but we have much lower signal to noise data. So in this case, we don't want to try and do a Fourier transform to try and pick out that lag directly. But a more meaningful question is, what are the range of time lags that are consistent with the data that we do have? And we can address this question with a similar statistical approach. This one was first presented by Zogby et al. In 2013 to work around the gaps in NuSTAR and Suzaku light curves from the low Earth orbits of those spacecrafts. To do this, we apply the Gaussian process simultaneously to the light curves in the two energy bands. And to do that, we stack the data vectors together, light curve 1 and light curve 2, just x and y. And if we do that in our Gaussian process and the associated likelihood function, it splits the covariance matrix into 4 quadrants. On the major diagonal, we just have the autocorrelations of light curve 1 and light curve 2. But then on the minor diagonal or the off diagonal of this matrix, we have a similar covariance matrix, but this one is described by the cross correlation of the two light curves. And in this case, the time lag is expressed by the parameters of the model that describes that cross correlation function. The model time lag can either just be a simple time shift, that would be the simplest model, or it can be a lag as a function of Fourier frequency, or we can even fit an impulse response function derived from a physical reverberation model directly to data in the time domain without having to venture into the sometimes scary Fourier domain. And this is what we get when we apply this technique to the Einstein cross. So this is just taking image number 1 here. We're looking for the time lag between the broad I and K band and the continuum dominated band. So that's 1 to 4 keV in the rest frame and 4 to 7 keV in the rest frame, but of course redshifted. We model the autocorrelations just by simple power law, power spectral densities. And then the cross correlation, we just put in a constant time lag. And then we can draw samples from our likelihood function using MCMC or nested sampling or whatever your favorite sampling method is to eventually obtain the posterior distribution of the time lag. So these are the time lags that are consistent with the data. And we find we can actually pick out a time lag of around 1600 seconds here. But in a multiply lens quasars, we have additional constraints. We don't just need to measure the time lag in between the I and K and continuum in image 1, but we can measure time lags between images. For example, we can take the continuum from image 3 and the I and K emission from image 1. Now, when we measure the lag between different images, we need to take into account the time delay that arises from the lensing itself. So different light paths around the gravitational lens will impart time delays on the light curves. And that will be superimposed onto the intrinsic I and K reverberation lag. But we can simultaneously model or fit the lensing time delay with the I and K time delay to marginalize over all of that uncertainty. And we do that by, as well as looking at the continuum and I and K bands, we look at the broadband variability between those two images as well. That should just be the simple lensing shift. Now, the signal to noise in image 3 is much lower than in image 1. So the lag you can see here is somewhat less constrained, but it's at least showing a proof of concept that we can do this study. And we can take the simultaneous constraints from image 1, image 3, and the cross time lag between images 1 and 3 to get a final constraint on that lag. So by doing all of this fitting simultaneously, we can put together this final distribution of the time lags in the Einstein cross measured with Chandra. So we come up with a time lag of 1600 seconds plus 600 minus 300 seconds for a 1 sigma error bar there. Now, does this 1600 time lag make sense? Well, to test that, we can build a model of the reverberation time delays we expect from the spectrum that we measure. And from that model, we predict that the lag should be 1500 seconds. So we're pretty much there. And we can compare the Einstein cross lag with the sample of the I and K lags from Seyfert galaxies. And here it is. We can see it fits that relationship that we typically see. This is from Erin Kara's sample of I and K lags between the black hole mass and the time lag. So to summarize, we can use these statistical frameworks and Gaussian processes to extend our measurements of reverberation beyond the local universe to see the lag in radio galaxies and lensed quasars. And this will be really important with future high-resolution X-ray missions, such as LINX, to probe accretion physics onto those growing black holes in quasars. Thank you.
Thank you very much, Dan, for that very interesting talk. We have a number of questions in the Slack from J. Michael Burgess. We may not have time for all of them, so I will ask one. You can respond to the others there in the Slack channel.
Sure.
Are you actually using the typical Gaussian process, Gaussian likelihood, or do you sample all the covariates and pass it through?
See if I understand that. So yes, we're using the typical likelihood function that's used in the Gaussian process, and then the model forms parameters within that we're then applying to the data through the Gaussian process likelihood function.
We have some similar questions on the method there in the Slack channel if you feel like responding to them there.
Yeah, sure thing.
We also have a question here that you can answer during the next speaker, Dan. Ask the next person to start sharing their slides. Our next speaker is Lacey West from the University of Arkansas, and they're going to speak to us about the large deficit of high mass X-ray binary emission from luminous infrared galaxies, the case for the circumnuclear starburst ring in NGC 7552. Lacey, there you go. Excellent. Yes.
So again, yes, thank you for hosting, Rodolfo, and everyone for tuning in. Again, my name is Lacey. I'm going to be talking to you about the deficit of HMXB emission from luminous infrared galaxies, with a particular focus on this NGC 7552. The X-ray emission deficit in LERGs comes from the expectation that, in general, your galaxy integrated X-ray luminosity is going to scale with your star formation rate. So as you have more star formation, you expect more emission from HMXBs in general. And here is an example from Lamer et al. 2019 that I will compare our results to at the end here. So you'll see that again. LERGs in general have X-ray emission that's about 10 times lower than expected based on relations such as these, and with distances typically greater than 50 megaparsecs, it's hard to identify the reason for that deficiency. This case, though, with NGC 7552, it's a relatively nearby LERG with a distance at about 20 megaparsecs, and the X-ray emission is indeed about 5 times lower than we would expect based on those relations. And you can see this central chunk here has been resolved in the infrared into these discrete star-forming knots in 1 through N9 by Brandel et al. 2012, who estimated each of the ages to be young, so about 5 million years, and highly obscured and relatively high metallicity, so about 2 solar. We were able to get Chandra observations, and here's the image in 2 to 7 keV, again, of that central region. And we were able to resolve, several point sources you can, kind of differentiate there. And it did reveal a major deficit in the X-ray emission from at least 2 of the 3 most powerful star-forming knots. So you can see in the infrared, N1 and N2 are really powerful, and then basically not emitting in the Chandra 2 to 7. So what are some reasons for that X-ray luminosity deficiency? One could be a high obscuring column, especially in the relatively low energy range covered by Chandra, so less than about 7 keV. You could have high metallicity that actually suppresses the formation of HMXBs, so they actually are not present. Or stellar population age could also be a factor, where those infrared luminosities are high due to recent basically bursty star formation behavior, and the HMXBs just haven't had a chance to form.
2 minutes.
We have ruled out the presence of the HMXBs, basically that obscuration factor with new star observations. In that 12 to 25 keV, you would expect to see if the emission is more immune to the obscuration effects. So you would be able to see them if they were there, and we have found that they are not. So I'm going to skim over this, but we were able to extract spectra from these individual Chandra sources, and they do seem to be consistent with X-ray binary, just a simple power law. This says future work, but we have done quite a bit of this already. So we're comparing the star formation knots and the X-ray detected sources I just mentioned with this Lamer 2019 relation. And in addition, they have a 2020 relation where they have adjusted for metallicity. So by comparing these sources with that relation, we are finding that metallicity plays a role, but may not exclusively explain the deficit. So we're continuing to explore that along with stellar population age and other source types, potentially supernova remnants, and et cetera. So that's where we are now. And I might have time for one question.
Definitely, we have time for one question. If you have a question, please put it in the Q&A or add it to the Slack if you'd like to carry on the conversation there. We have a question here from Rafael Martinez Galarza saying, thanks, Lacey. Could the reason why some of the knots do not emit yet be that the X-ray binaries have not formed yet?
Yes, definitely. They are young, so they're about 5 megayears to 6.3 megayears in that range. So it's really young, especially if the star formation hasn't been steady state or the ages. There has been some talk about the ages, absolute ages not being totally reliable, but the spacing being more reliable. So that's one thing that we're exploring. Good question. Thank you.
Awesome. Thanks again for an excellent talk. If you have more questions for Lacey, please put them into the Slack channel. Thank you. Our next speaker, if they can begin to share their slides. Our next speaker is our invited speaker, Adi Foord, from Stanford University, Kavli Institute of Particle Astrophysics and Cosmology. Is going to talk to us about identifying closely separated and low count sources in Chandra observations.
Great. Can you see my screen?
Yes.
Okay, great. So hi, everyone. My name is Adi Foord. I'm a PORAP postdoctoral fellow at Stanford University. I'm really excited to be speaking at Chandra Data Science 2021. Today, I'm going to be speaking about a tool that I developed to identify closely separated and low count sources in Chandra observations. And a few of the interesting sources that I've identified are actually shown in the background of this title slide, and some of them will make appearances throughout this presentation. So today's talk will be focusing on Baymax, which stands for Bayesian Analysis of Multiple AGN and X-rays. And for those of you who don't know, Baymax is also a robot from the Marvel universe, which I incorporated into the logo. So you'll be seeing this robot on a couple of the slides. This is a tool that I have developed over the past couple of years to analyze Chandra observations for systems with multiple AGN, as the title of the code infers. So Baymax allows for a quantitative and statistical analysis on whether an X-ray image is composed of one or multiple point sources. And this GIF is showing 10 Chandra simulations. Half of these are observations of dual point sources, and half of them are observations of single point sources. And it's bolding the systems that are actually dual. So Baymax was able to correctly identify each of these systems as likely being composed of two versus one thing. And the simulations of the dual point sources have a large range of separations between the 2 point sources, as well as a large range of flux values. So before I get into the nuts and bolts of how Baymax works, I want to give some context for why this tool was created in the first place. So most of my research focuses on dual AGN and learning more about the connection between their activity and their environments. So in this figure, I'm showing a scenario of two galaxies that are in the process of merging, and each galaxy has its own central supermassive black hole. So the dual AGN stage is a stage of the merger where your two supermassive black holes are actively accreting and they're kiloparsec scales apart from one another. So this is the population that I mostly study. It's a precursor to binary supermassive black holes where the two black holes are gravitationally bound. And then of course, the phase where they actually merge. So compared to the observable frequency of galaxy mergers in our universe, the number of dual AGN that have been detected actually remains relatively small. So in this figure, I'm showing confirmed dual AGN that I've pulled from the literature, where the marker denotes the detection wavelength. The y-axis shows the projected physical separation, and the x-axis shows the redshift. So as you can see, there's less than 50 or so confirmed dual AGN to date. This was created about 9 months ago, so plus or minus a handful of data points. Most confirmed dual AGN are X-ray detections, and most confirmed dual AGN have physical projected separations larger than a kiloparsec. So the rather small sample size of confirmed dual AGN really limits our ability to understand supermassive black hole growth and evolution, as well as the host galaxies' growth and evolution. So because of this, a lot of my work is focused on expanding the known number of dual AGN. So some of the most robust methods for finding dual AGN is using radio or X-ray observations. This allows for a direct detection. So you can confirm a dual supermassive black hole observationally if both black holes are actively accreting and if you have the necessary resolution. So radio observations allow for resolving on the smallest scales. And on the left-hand side, I'm showing an AGN pair that has a projected separation of 7 parsec. And this is resolved using the VLBI. If you're going to be using X-rays, you may want to use Chandra just because of its superb angular resolution. So on the right-hand side, I'm showing a dual AGN that was detected using Chandra. And in the left panel, the Chandra detections are overplotted on the optical image. And if you compare this field of view to XMM's field of view, you can see why here it was really necessary that you had Chandra. However, unfortunately, as the angular separation between your dual AGN nears the instrumental PSF, it becomes very difficult to resolve even with Chandra. So here I'm comparing an X-ray simulation of a single point source as observed by Chandra to that of a dual point source as observed by Chandra. And the dual point source simulation has an angular separation of 0.3 arcseconds. So by eye, it's really hard to discern here between the single and the dual point source. So currently, we're really limited by the angular resolution of our telescopes in identifying dual AGN. And this is one of the main reasons that the population of confirmed dual AGN remains so small. So this issue is the motivation for my research, where the development of a tool that could analyze a Chandra observation and tell you the likelihood that you were looking at one versus two things would be extremely useful. So Baymax allows for this statistical analysis, and it does so using a Bayesian framework, and in particular Bayes factor. And luckily on Tuesday, Johannes did a great job of detailing Bayesian statistics, Bayes factor, and a few other terms that I'm about to mention. So hopefully this supplements my explanation of how the code works. So Bayes factor represents the degree to which you're favoring one hypothesis over the other. And I'm showing the analytical form of Bayes factor on this slide. So for all of my analyses on dual AGN, I'm comparing a single point source model to a dual point source model. And values greater than or less than 1 generally will tell you which model is favored. So within your integral, you have your likelihood density and your prior densities. Oops, sorry. So regarding the likelihood densities, Baymax calculates these by generating likelihood models for single and double point sources. For a given observation, Baymax will model the unique PSF, which we heard a little bit about this today, depends on many different parameters like the date of the observation, the pointing of the telescope, the RA deck coordinates of your actual source, etc. And it does so using a software called MARCS, which we also heard about today. And MARCS contains detailed models for Chandra's high resolution mirror assembly. The code uses Poisson statistics to calculate the likelihoods, where for n data bins, it computes the likelihood that the data would come out as it does. So here, m is the number of counts that the model predicts in bin I, for a given parameter value theta, which is defined by the prior distributions, and D is the number of counts the data has in bin I. So luckily, with X-ray telescopes and with Chandra in particular, we don't have to really bin our data. We can compute the likelihood for each detected event. And then regarding the prior densities, examples of parameters in the prior vectors for the dual point source model include the spatial sky X, sky Y coordinate of each source, as well as the count ratio, which is denoted by parameter F. And this represents the number of counts the secondary has with respect to the primary, as well as the background fraction. So this represents the number of counts associated with the background component as compared to a point source component. So the distribution and the ranges of each distribution for the prior can be set by the user. So here I'm showing examples of a flat prior for the count ratio parameter, meaning that any value on this range is equally probable, as well as a Gaussian distribution for the background fraction parameter, where here you can weight certain values with higher probabilities. So once the code has generated likelihood models for single and double point sources that are unique to the observation, and the priors have been defined, which can be either user-defined or non-informative. So it's flexible that you can incorporate pre-existing information that you may have from optical or infrared observations. For example, the code calculates Bayes factor using nested sampling. And so just briefly, this is an MC sampling technique that allows you to more efficiently calculate the Bayes factor versus actually trying to calculate that integral, which computationally is way too time consuming. And then lastly, using an MC-MC algorithm, and specifically PyMC3, the maximum likelihood of parameters and their uncertainties are estimated. And as of right now, the Bayes factor calculation is a separate calculation from the MC-MC posteriors calculation. The idea is that you may only want to run this more in-depth, time-consuming analysis of likelihood space if you have an interesting source. But you can, of course, run that MC-MC function on any source that you want. Lastly, for every system that the dual point source model is favored, we run tests in false positive space in order to quantify what a strong Bayes factor is, which will be unique to the observation. So here I'm showing results from running Baymax on thousands of simulations of on-axis dual point sources with various separations denoted by R and count ratios denoted by F. And the z-axis here is showing the log of the Bayes factor in favor of the dual point source model. And the dark blue areas denote where Baymax was not really sensitive to the correct model. So as you can see, the Bayes factor strengthens as a function of increasing separation and count ratio, which makes sense. The two sources are much more obvious in that region of parameter space, and it decreases with decreasing separation and count ratio as well. So on average, for observations with 200 counts, we can probe angular separations below 0.5 arcseconds at count ratios larger than 0.4. This graph will look different for a system with 700 counts, where we can start pushing separations as small as 0.35 arcseconds or so, or an observation with 10 counts where you're not really sensitive to a lot of parameter space. And as well, this will look different for an off-axis observation where you start to lose sensitivity in certain spatial directions because the PSF of Chandra becomes a little bit more elliptical as a function of off-axis angle. So thus far, Baymax has published on 3 different analyses of merging and interacting AGN. The first was analyzing Chandra observations of the lowest mass dual AGN candidate to date, and we ended up not finding any evidence for dual AGN. The second was analyzing 12 candidate dual AGN that were candidates based on analyses of their optical spectra. And the most recent was searching for dual and triple AGN in a sample of nearby triple galaxy mergers. So I don't have time to get into the details of all of them, but I want to highlight some of the results so you get an idea of how Baymax works and its capabilities. And as well, I can highlight some of our interesting findings on the environments of dual AGN. So this is an example of a few galaxies from Baymax's analysis on 12 candidate dual AGN. They were all targeted as dual AGN candidates based on an analysis of their optical spectra. And on the left-hand side, I'm showing the optical data for these candidates. And on the right-hand side, I'm showing the follow-up Chandra observations that were taken for them. So we did have prior knowledge of where a primary and secondary AGN may be sitting based on the previous optical spectroscopic analysis. And so we used that information to define locations, informative locations for where primary and secondary AGN may sit, which I'm showing in red and orange boxes here. But I do want to emphasize for all analyses that we've used Baymax on, we also run it using non-informative priors. So there, the X-ray point sources can sit anywhere in a given field of view as defined by the user. So once a system is found to have a Bayes factor that strongly favors the dual point source model, Baymax can probabilistically assign each count to a different model component and will return posterior distributions for various parameters. So on the left-hand side, I'm showing the unbinned Chandra data for this one source, where counts likely associated with the primary are plotted in red circles, and those most likely associated with the secondary are plotted in orange squares. And then on the right-hand side, I'm showing the joint posterior distribution for the separation and for the count ratio. Because Baymax can probabilistically assign each count to a different model component, the code can actually sample from the posterior distributions and create spectral realizations of various components. So a spectral analysis with Baymax is quite powerful because it allows you to individually analyze spectra of closely separated X-ray components. And a spectral analysis is also useful because you can analyze things such as the flux ratio, whereas right now the posteriors returned by Baymax gives you information on the count ratio. So here I'm showing spectral fits of various spectral realizations of a primary and a secondary X-ray point source. And one of those spectral realizations are overplotted in black. And so for most of our dual AGN studies, we define an AGN luminosity criterion, which is so we define a luminosity, and any X-ray point source needs to meet this luminosity in order to be classified as an AGN. The idea being that at values below this luminosity, you are susceptible to contamination from X-ray binaries. So using the results of Baymax, we have gained interesting insight on the environments of dual AGN, specifically pairing our X-ray results with complementary multi-wavelength observations. So here I'm showing a sample of 6 dual AGN candidates that were visually identified as merging in their HST data, and I'm showing the HST data on the left-hand side. And this sample includes 2 systems that Baymax favored the dual point source model for, and that had a primary and secondary that met that AGN luminosity criterion when the spectral analysis was carried out. So one of the things we looked at was how the extragalactic hydrogen column density, which is a parameter you can get in the X-ray spectral fits, varied as a function of the physical separation between the mergers. And just in case anyone is unfamiliar with this parameter, this is something you can fit for in the X-ray spectral fits, and it's a measurement of the gas density surrounding the AGN. So there are only 6 data points, but the data suggest that AGN pairs may prefer gas-rich and closely separated environments. And this is something that simulations as well as other analyses, observational analyses, have found as well. So this is the type of stuff that I want to do in the future with much larger samples. The most recent analysis that we used Baymax on was analyzing a sample of triple galaxy mergers to search for potential triple AGN systems, and as always, more dual AGN. So triple galaxy mergers and triple supermassive black holes are interesting for a handful of reasons. But given that thus far, we only have one serendipitously discovered triple AGN, we didn't discover it, another team discovered it, but I was definitely eager to find more triple AGN. So here I'm showing the results of using Baymax to analyze Chandra observations of 7 triple galaxy mergers, which were identified in SDSS. And we confirmed that one triple AGN that had already been discovered We discovered 4 new dual AGN, which was really exciting. And then there were a handful of systems that either had no evidence for an X-ray AGN or had a single AGN. And so here I'm showing the unbinned Chandra data again for these systems, where the markers denote the component that the counts are most likely associated with. And I'm overplotting the optical contours of the merging galaxies. So we found this variety in the number of X-ray AGN, all the way from likely having no X-ray AGN up to having 3. And this variety allowed us to look into possible links between AGN activity and differences in their environments. Once again, so in particular, we looked at the levels of obscuration in each system as measured in the mid-IR wavebands via WISE. So this plot is showing the WISE1 minus WISE2 color versus the extragalactic hydrogen column density for systems that had suitable WISE coverage. And the numbers next to each marker denote how many X-ray AGN were detected in each system. So we found this trend between the levels of gas and dust in these systems, whereas the W1 minus W2 color increased, so did the NH levels. This isn't incredibly surprising. It's likely reflecting that the motions of gas and dust are coupled in these environments, and large amounts of both can be efficiently funneled into the active central region. But interestingly, we found that the triple AGN system had the highest levels of gas and dust, while the dual AGN all had lower levels. And given that supermassive black holes grow and are triggered to AGN through the accretion of cool gas, it's possible that triple merger systems with higher levels of nuclear gas will have more AGN. So this is something that I definitely want to do in the future with a much larger sample of triple galaxy mergers. So moving forward, I'm particularly interested in pairing the power of X-ray and IR observations. And for dual AGN studies, X-ray and IR observations really complement one another. So in particular, for any dual AGN detected by Baymax in the X-rays, follow-up via high-res IR observations can identify stellar nuclei associated with each AGN, as well as allow for obscuration measurements and mass ratio measurements of the galaxies, etc. So this is a really great example of that. Baymax was used to analyze a sample of merging galaxies that had both Chandra and high-res IR follow-up with Keck. And this is a large survey being led by Mike Koss. So here I'm showing an X-ray observation from one of the merging systems, and it was targeted as a merger based on this low-res optical image where they resolved this large tidal tail. So it's kind of a signpost of some kind of merger. So we analyzed the X-ray observation with Baymax, and here we were using non-informative priors. So we didn't have information on where a primary and secondary AGN could be sitting. And now I'm showing you the results from Baymax. So Baymax strongly favored the dual point source model. And in the X and the cross, it's showing the locations that the code thinks the primary and secondary are. And here the markers are color-coded to just denote soft and hard photons. So excitingly, when we compared the results from Baymax with the high-res IR follow-up with Keck, there were 2 stellar cores that were resolved at the same locations that Baymax found. So Baymax has been used on other sources in this sample, and hopefully this study should be published sometime soon. So returning to this plot, there really are only a handful of confirmed dual AGN, and I've tried to, over the past 2 or 3 years, to contribute to this field and add more data points to this plot. Although the stars right now aren't necessarily in an interesting region of parameter space, if we change the axes instead to be separation versus count ratio, you can see that Baymax is filling in a region in parameter space that wasn't really accessible before the code was developed. The future of dual AGN studies is really going to rely on large-scale X-ray surveys, and this is what I'm currently working on while at KaiPAC. So please look out for new studies that will be published soon. So I also want to highlight that Baymax can be used for so much more than just multi-AGN systems. anytime you're interested in whether your Chandra image is composed of one or multiple X-ray point sources, you can use Baymax. So most recently, it was used to analyze the X-ray emission of a high redshift quasar. And this was a project led by Kate Napier, who is a PhD candidate at the University of Michigan. Without getting into the specifics, this is a peculiar case of a high redshift quasar with bright radio emission from the lobes. And so I'm showing the radio image on the left-hand side, where you have a core and two lobes. And one of the main questions of the analysis was whether the lobes were X-ray emitters as well, and if so, what the luminosity was. So here I'm showing the Chandra observation that they got for this source. And given that there are less than 60 counts, it was quite difficult to tell whether the lobes were emitting in X-rays as well, and if they were, if there was a similar position angle as you saw in the radio observation. So this was a perfect opportunity to use Baymax. Baymax analyzed this observation, and here they were comparing a single point source to a triple point source system. So either just the core emitting or the core and the two lobes. And so
2 minutes, sorry.
Oh, thank you. And so just jumping straight to the conclusions, Baymax highly favored the triple point source model. And once again here, I'm showing the counts with different markers depending on which component they are associated with. So as I previously mentioned, while at KaiPAC, I'm focusing on analyzing large X-ray surveys with Baymax, but others are currently using the code, and I've just listed a few of the projects on this slide. Excitingly, there are projects using Baymax for things besides dual AGN, which I really hope can happen. So that being said, Baymax is on GitHub. If you have an idea for Baymax, shoot me an email and I can give you access to the code. My goal was always for Baymax to be public. And I've been working on formatting the code so that it's user-friendly and easy to use. So I'm hoping there will be a public version available within a month or so. So please stay tuned. Okay, so I've reached my final slide. I'll just quickly say that Baymax allows for a quantitative and statistical analysis on whether an X-ray image is composed of one or multiple point sources. And pairing results from Baymax with available multi-wavelength data, I'm discovering new dual AGN and I'm learning more about their environments. So Baymax can be used for a lot more than just dual AGN science. And I do have plans to expand Baymax to other X-ray PSFs. So this includes XMM or NuStar or LINX. Obviously, the PSFs for all of these instruments are very different, and so you will be sensitive to different kinds of sciences, but I still think you can do useful things with Baymax on all of the data sets observed with these telescopes. And Baymax should be public soon, but if you have an idea for Baymax and you want to use the code right now, let me know and we can talk more. So thank you so much, and I'll take any questions.
Thank you, Adi, for that excellent talk. You have several questions. I'm going to ask, we have 5 minutes, so we have lots of time for those questions. The first question I want to point out from Keith Arnaud, who asks, if you see two X-ray sources, how do you know that it's a dual AGN and not an AGN with a jet? Yeah,
that's a really good question. And the answer is you don't from the get-go. All you know is that there's likely not just one thing there. So in particular, follow-up with a spectral analysis can possibly help. So you can compare the spectra of the second component and see if it's consistent with what you might expect with an AGN or not. But also in this case, follow-up with multi-wavelength observations can also be helpful. Is there, what's the radio emission look like in that area, et cetera. But it's definitely an important point that Baymax on its own is comparing 2 versus 1 point sources, and that isn't, saying that you definitely have a dual AGN at any point.
Right. We don't have a model for a jet, I guess.
Not yet, but I mean, I can add it to my list.
The next question is from J. Michael Burgess on the Slack channel. If you use uninformative priors, is there a reason to use Bayes factors over likelihood ratios, which are approximately equivalent under those conditions?
Not necessarily, no. I mean, the whole reason for Bayes factor was because I wanted this to really be a multi-wavelength analysis. So I did want the ability to take Hubble images and fold in that information into the code. But yeah, if you are using non-informative priors, the priors won't necessarily add much, depending on what your data set looks like.
Awesome. And then we have a question from Vinay Kashyap, who says, nice talk. 2 questions. Have you done the separation/ratio sensitivity test using EDSER, the subpixel event repositioning applied? And does it make a difference for small separations smaller than 1 pixel?
So all of the data sets do have the EDSER algorithm applied, which is why, as of right now, Baymax is set up to only work with ACIS-S and ACIS-I observations. However, I would love to get it set up with HRC observations as well. Most of the sources I've analyzed thus far have been in the low count regime. And because of that, you really don't see a difference applying the EDSER algorithm or not. This might be different if you have a lot more information in your observation, but thus far, it hasn't made a big difference, but it is automatically applied to any observation that Baymax analyzes.
The second part of Vinay's question is, have you looked at the sensitivity of the power of the method to the adopted prior, because Bayes factors become strongly dependent on priors at low signal?
Yeah, definitely. So that's one of the reasons why for all of our analyses, we do a run with non-informative priors, because like you said, especially in the low count regime, your priors can have a really large influence on the Bayes factor and on the posteriors. That being said, all of our priors for location are flat. So we're not using Gaussian priors, for example, they're flat. And what we mostly do is we constrain just the range, like the XY range of where it is. And because of that, our results have been consistent between using non-informative and informative priors thus far. That would definitely be different if you had a peakier prior distribution, for example, that was much more constrained, if you only had 20 counts. But that's why we're careful to not do that.
This next question, we have time probably for these last 2, is from Rafael Martinez Galarza. Nice work about your column density estimates when fitting the spectra. Do you account for any gas that might not be associated with the AGN, but perhaps from interstellar or intergalactic fields?
So for all of our spectral analyses so far, we haven't. One of the main reasons being that we are working with sources with under like 200 counts usually. And so fitting with a simple like absorbed power law has been fine. And, fits become degenerate pretty quickly when you don't have a lot of counts. But now that I am analyzing really a large survey with thousands of AGN, the spectral models that I'm using, I think will have to start changing, because you can start accounting for other components that, when you have more counts. But thus far, I haven't, no.
Great. There are a few more questions in the Slack. I'm going to let you answer those there if you feel like it. Thank you, everybody, for the questions. That's all the time we have for the invited speaker. Thanks again, Adi Foord. Our next speaker, if you can begin sharing your slides, is Aswath Suryanarayanan. And they are coming to us from Columbia University and will talk to us about the analysis of the cosmic X-ray background to constrain oxygen abundance in warm, hot intergalactic medium.
Hello, everybody. Can you hear me all right?
Yes, I can.
Great. Yes. So, hello, everybody. I'm Aswath Suryanarayanan, and I'm a third-year student at Columbia University. Over the course of the past academic year, I analyzed the cosmic X-ray background to constrain the oxygen abundance in the warm hot intergalactic medium. So, measurements of the universe at high redshift indicate a baryon fraction of around 4% of the total matter energy density, but local universe measurements indicate around 2% of baryon fraction, as you know. So, how do we bridge this discrepancy? Cosmological hydrodynamical simulations under CTM paradigm suggest that this discrepancy is likely due to the presence of a warm hot gas in the IGN. This WIM is very difficult to detect and study, and thus the in detailed analysis of the baryon deficit is very hard. And the hot cores of the WIM filaments can only be detected by soft X-ray excitation of highly ionized elements in the plasma, like oxygen-7 and oxygen-8. So there are a few ways to detect the WIM, and the primary ones are thermal emission and resonant absorption, both of which are sufficiently weak that detection of such emission is prohibitive for current X-ray telescopes. And there is insufficient neutral hydrogen in the warm hot intergalactic medium for using Lyman alpha absorption of spectra of distant quasars. So what do? So we detect resonant scattering of light from distant sources by layers, and this is doable because the net effect of resonant scattering and the precursor, that is the resonant absorption of spectra of bright background sources, cancels out after integration over all directions. And the cosmic X-ray background is overwhelmingly made of bright point sources, which can be resolved, and the remaining unresolved spectra displays emission due to the resonant scattering, which has feature amplitude proportional to line of sight column density and not emission measure, which makes it possible for us to understand global baryon density properties independent of local temperature and density. And in this particular diagram, you can see the difference between thermal emission, resonant scattering, and resonant absorption. So the oxygen-7W resonance line is prominent, located in the soft X-ray range, and is resonantly scattered by the WIM. And with a survey of around 2 degrees squared and 5 megasecond exposure that can suppress point sources, we can trace the intergalactic oxygen independent of temperature and density of the intergalactic gas. This research is primarily a proof of concept of that statement. So we use the largest deep survey performed by Chandra, the Chandra Cosmos Legacy Survey, and we obtained the unresolved CXP spectrum of the CCLS, and we use XSpec for spectral fitting. So the major components of the unresolved CXP spectrum that we model are the local hot bubble, which we model using an APEC, the circumgalactic halo, APEC and an ISM absorption model, unresolved point sources, power line and ISM absorption model, and the WIM, which we figure out how to model. And
2 minutes.
Any such model component will join a multiplicative ISM absorption model. So we perform extensive analytical calculations to estimate the WIM model and associated components, and we obtain the intensity as a function of energy, and further analysis of which leads to the notion that the WIM scattering, resonance scattering, is best represented by a broken power law. And we also identify the necessary computations to obtain the oxygen-7 abundance ratio from flux. So this is the unfolded spectrum with each model shown individually. And this particular table has the values of all model components. And primary concern of ours is the normalization of the broken power law. The computations which we saw in the previous slide indicated and led to the result that the oxygen-7 abundance ratio that we identify is of the order of 3. So this research is a major proof of concept of the notion that due to the properties of the oxygen-7W resonance line, with a survey of some particular properties that can suppress the point sources, we can trace the IgM oxygen independent of temperature and density of the IgM. So we have established the feasibility of this particular project. And obviously, the oxygen-7 abundance ratio obtained is bound to decrease manifold due to the considerations involving the thermal emission from the WIM, the SWCE, the a closer analysis of foregone emission from the CGM and LHB. So the most important point I'd like to cover here is that the entire Chandra archive satisfies the aforementioned properties, and thus a future meta-analysis along the same lines as this research, involving a combination of several Chandra spectra with much higher total exposure time, will yield stricter constraints to WIM 07 abundance and consequently baryon density. Thank you, and if you have any questions, feel free to ask.
Thank you very much, Aswath, for that. We don't have time for, that was a perfect 5 minutes. We don't have time for questions to take live, but if you have any questions, please do add them to the Slack channel, and I'm sure they can be addressed there. So I'd ask our next speaker to start sharing their slides. Our next speaker is Hui Yang, coming to us from George Washington University and talking about machine learning classification of Chandra X-ray sources, accounting for measurement uncertainties and confusion.
Can you hear me well?
I can hear you, yes.
Can you
Great.
see my slides?
I can see your slides.
Okay, great. Thank you for the introduction. Hello, everyone. Thank you for having me here. So my name is Hui Yang, a rising fourth-year graduate student at the George Washington University. And I would like to thank for the committee for offering me this opportunity so that I can talk about our machine learning classification pipeline of Chandra X-ray sources with recent development of accounting for measurement uncertainties and confusion. And here are my collaborators. So why do we need machine learning classifications? To start with, we have entered an golden era of multi-wavelength, multi-epoch, and multi-messenger astronomy. And with the advent of next generation observatories, we are witnessing an explosive growth not only in the volume of the not only in the volume but also in the complexity of data. So the increasing number of detected sources of detected X-ray sources, which are mostly discovered serendipitously, prevents us from analyzing all of those sources accurately with manual investigations, leaving most of them remained unclassified. For example, the recent EROSITA survey found more than 1 million X-ray sources, and Chandra Source Catalog version 2 has detected more than 300,000 X-ray sources. And what's more frustrating is that most of X-ray sources look very similar to each other, and they are relatively faint and hence difficult to distinguish them from each other. And they are most of the time the sources that we want to classify. So that's why we need to develop an automated and efficient way to classify astronomical sources, and one solution is to use machine learning algorithms. We develop a machine learning approach to multi-wavelength classifications of X-ray sources, aiming to address all of the obstacles I mentioned earlier. The first and the foremost part of the supervised machine learning method is the training data set, which is a set of labeled sources that we use to fit the model. We have constructed a sample of almost 3,000 identified X-ray sources by cross-matching Chandra source catalog with literature verified sources, which include 9 sources types of X-ray emitters. But they are very imbalanced among different source types. We also extract multi-wavelength information from catalogs like Gaia, 2MASS, and WISE to construct up to 31 features that we use for the pipeline. We not only include the multi-wavelength properties for the training data set, but also we try to incorporate like temporal properties as well. We add 2 X-ray variability features for both the long-term and short-term scales in our training data set. And you have heard more details from Oleg's talk earlier today. Here I show 2 plots of 2D slides of the high dimensional feature space of our training data set to give you an idea of how our training data set look like. The 2 plots are made by our visualization tool available on our X-Class website, and more details were presented by Jeremy earlier this week. So the different colors indicates different type of sources. For the traditional classifications, we rely on those 2-dimensional parameter plots to separate different classes of sources. On the left, you can see that different classes of sources seem to separate from each other, while on the right, the sources are more overlapped. It becomes impossible to even comprehend the dependencies when the data set is getting larger and the dimensionality goes up. On this slide, on the left-hand side shows the workflow chart of our current pipeline. First, both unclassified data and training data are fed into a Monte Carlo machinery to take into account of measurement uncertainties, and which I will talk about in the next slide. And we also estimate the confusion probability to account for the confusion. So as a field-specific absorption and extinction is applied to AGNs on the training data set, since AGNs are located outside of the plane, which makes them appear very different when viewed through the galactic plane. We also use the SMOT algorithm to handle the large imbalance of source types in the training data set. Finally, the training data set will be trained with the random forest model, and the unclassified data can be fed into the classifier to obtain the probability to any of those 9 classes. The whole pipeline is compiled in Python, where most of the machine learning algorithms are available from the scikit-learn package. In the past, most of the machine learning classification works in astrophysics do not take into account of measurement uncertainties, so that the uncertainties of the classification results can be properly obtained. Very recently, there are some machine learning algorithms available which indeed take into account of measurement uncertainties. For example, the probabilistic random forest algorithms. Here, we do it in a different way by applying the Monte Carlo samplings. Here, it shows a distribution of the probability density of one of the features in the training data set, which is the broadband X-ray flux. And we sample the flux from measured values and their uncertainties. And we do it for other features as well. For each sampled training data set and the unclassified data, we will get a classification result from the random forest classifiers. In the end, we will combine all of the classification results so we can get a distribution of probability assigned for a certain type of class. And this plot, this histogram shows the probability distribution of an X-ray source to be classified as a high mass X-ray binary. And the vertical black line is the probability without the Monte Carlo sampling, where the uncertainties is not involved. So we can also plot the histograms for other classes as well. We have evaluated the performance of the machine learning pipeline using the confusion matrices of cross-validation, where each row presents the fraction of sources in the predicted class, while each column provides the fraction in an actual class. The more diagonal this matrix is, the better the performance. On the left is a confusion matrix for all sources in the training data set, while on the right for the confidence classifications. Our machine learning model has reached an overall accuracy of 88% and up to 97% for the confidence classifications. But we can also see that not all of the classes are being classified equally well. The plus and minus signs here are coming from the Monte Carlo samplings from measurement uncertainties. Now we can take a look at the impact from taking into account of the measurement uncertainties. Here I plot the distributions of classification probabilities per class for each column and for 3 Chandra X-ray sources for each row here with Monte Carlo samplings. For each histogram, the probability ranged from 0 on the left to 100% on the right, and the vertical line shows the classification probability without accounting for the uncertainties. For the first example in the first row here, we find the classification results are totally different with or without the Monte Carlo samplings. The Monte Carlo trials result in a classification of high mass stars where you with a probability of 77% from the green histogram here, while the classification results without uncertainties involved label the source as a YSO with a low confidence from this black vertical line here. And the other two examples shows situation where the classification results can deviate if we don't include uncertainty information. Sometimes the probability can be underestimated for the second example here, and sometimes can be overestimated for the last example here. But we cannot say too much if we don't have the distributions of these probabilities, which we can evaluate the uncertainties for the classifications. In the current pipeline, we also try to take into account of confusions which might be caused by having spurious counterpart or matching to a wrong counterpart, especially in the very dense field. So we calculate the chance coincidence probability of having a spurious source within a certain radius of R, which will be the X-ray positional uncertainties in our case, given a source density rho of the field. And for the current Chandra source catalog version 2, the astrometry is not being corrected yet, and an systematic area of 0.7 arcsecond is being added. The relatively large X-ray positional uncertainties might lead to substantial chance coincidence probability in the dense field of galaxies. Therefore, probability of confusion has to be taken into account. To the first approximation, we can account for it in our Monte Carlo part of the pipeline by either including or without including the counterpart with its corresponding chance coincidence probability. A more advanced treatment is needed when multiple counterparts are plausible, and it will be more critical for sources from XMM, Swift, or Euro-theta with larger positional uncertainties. Here I show a comparison of the typical X-ray positional errors for X-ray sources for those different observatories. Another way we can alleviate the confusion problems is to trying to shrink the Chandra source position uncertainties by accounting for the astrometry when we develop our own Chandra source analysis pipeline. This CSA pipeline is developed to automatically analyze Chandra observatories, to analyze Chandra observations in a way that resembles Chandra source catalog pipeline. Since Chandra source catalog don't only include observations before 2015. We account for the astrometry by aligning the X-ray source positions to X-ray source to positions of sources from the Gaia catalog. So in the future, we are planning to correct the Chandra source catalog astrometry on the fly by matching Chandra source catalog sources to Gaia, unless this will be done by Chandra source catalog site soon. Here I show I present an example where the confusion comes into play. The plot on the left shows an zoom-in view of an X-ray source which is matched to two Gaia sources within its positional areas in a very dense field with a chance coincidence probability of about 9%. We apply the classification of these X-ray sources using these two different counterparts and without the counterpart. The results, the classification results show that it is confidently classified as a young stellar object with the nearest counterpart, while the confidence dropped a lot when we are using a different counterpart or without a counterpart. With all okay, thank you. With all the development, one downside of our pipeline is that it requires a huge computing sources. The current pipeline needs about 30 seconds for one classification by one core. So in order to classify all of the 300,000 X-ray sources from Chandra source catalog, with 100 Monte Carlo trials for each source, it takes about 28 years with a single core. And so we are currently using the high performance computing cluster packages at the George Washington University. And if we can make the full use of the cluster, the expected running time will be shrunk into about 1 day. So in the future, we plan to improve our training data sets for both Chandra and XMM, and the XM training data set is currently under construction. We want to expand the size of the training data set and to use more information for each source by including more sensitive surveys, multi-wavelength time domain properties, and distance information, where you can hear more from Stephen Chen's presentation next week on August 26th. And we also plan to make the classification pipeline and the CSA pipeline available to the public very soon. And we also plan to adopt the classification pipeline for use with XMM, Swift, and eRosetta catalogs. So I will stop my talk here and take any question. Thank you.
Thank you very much, Hu, for that very interesting talk. Very nice work. I'd like to open the questions to anybody who has a question for Hu. If we don't have questions now from the audience, I do have a question for you about so in the supercomputing use here, everything is still, everything is parallelized and that's what's giving you the speed up, or is it just the sheer computing power that's giving you speed up? Is there any attempt to parallelize this?
So we are currently trying to parallelize the pipeline because we are using this Monte Carlo sampling, so it can be easily parallelized. And yeah, that's the reason we can make full use of these multiple cores and speed up the time. Yeah.
And I didn't see the GPU nodes there. So it's also working on using GPU nodes to help speed up that calculation.
Yes.
Great. And so you mentioned that you have 300,000 sources from the Chandra source catalog, and you mentioned that you've done a similar thing for the observations since 2015. How many sources do you end up with for that post 2015 data?
So we haven't applied our CXA pipeline yet, but so we have currently several interesting fields, which we have our own Chandra data, which were observed after 2015, and we are using our CXA pipeline to analyze those interesting fields. Then we are planning to apply the pipeline to more sources. Yeah, that's our next step. Yeah.
Awesome. Any more questions? Please put them in the chat or here in the Q&A. I could ask you questions all day. I do have one more for you, though. I really like the confusion matrix, and I was looking at the neutron star binary, and all of that confusion there that you're seeing. Have you dug deeper into that to try to understand if it's because the neutron star, for example, in the neutron star binary one is dominating over the other, or what do you know what might be causing that confusion?
Yeah. So for some type of sources, the performance is not that good as other sources, type of sources. Those one with better performance are the one with a larger size in the training data set, and those you find it's worse is they have less number of sources in our training data. That's why next step we are trying to increase the training data by adding those rare type of sources. And like for low mass X-ray binary, so sometimes they can in like high state and low state, that also makes them like confused with other type of sources. And yeah.
Right. Excellent. Thanks so much for excellent talk again. And thank you very much for answering all my questions.
Thank you for your questions.
I'd like to ask our next speaker to start sharing their slides. Our next speaker is Aneta Siemiginowska, and she is going to talk to us about, she's from the Chandra X-ray Center and the CFA, and is going to talk to us about modeling and fitting in Python with Sherpa. You are muted at the moment, Aneta. There we go.
Okay, do you see my screen?
I see your screen.
Okay, and all right, you can even show me and allow the camera to point at me. Anyway, I have just 5 minutes, so this will be a very short description of Sherpa and basically introduction to Sherpa, what it is. And I put the current core team members on the right side and also the help desk. So if you send help desk questions, most likely Nick or Kenny will answer them. But please do, and we have 2 websites listed there. So what is Chandra? If I can actually scan this, okay. So Sherpa is a modeling and fitting application for Python, and we have the user interface and high-level functions, which are all written in Python. I'll talk about it a little more later. It can model 1D and 2D data, and it could model generic arrays, X-ray spectra, optical spectra, or images, as long as you provide the right coordinates. So you can have different types of data here. We have powerful model language for building complex model expression. We also have variety of fit statistics and optimization methods. The optimization methods are classical methods. They are very robust and tested with different type of data by users over 20 years. We also include Bayesian analysis methodology with PyBlocks, MCMC method, if somebody wants to be more modern. What's important is the support for WCS, the PSF convolution, and the standard X-ray responses, which you can use. The package is extensible to include user models, statistics, optimization methods. It's also included in different software packages, Python packages. And we moved the source code to GitHub, which means that the development at this moment is open and you can contribute. We have the contributions from different speakers, different developers in the past. So if you go on GitHub, you can see that. The more detailed Sherpa talks are on workshop pages. So this is the Sherpa 20 years milestone. We started very early with Chandra launch in December 1999 when we released the first Sherpa. And this package was C++ Fortran. 10 years later, almost 10 years later, we moved to Python. In the meantime, we have all these different trials. We built the solid C++ and Fortran-based, object-oriented. In 2015, this was another big milestone when we moved Sherpa development to GitHub, and we released the standalone Sherpa package for Python analysis.
2 minutes.
So 20 years of use. The source, the code is robust and well tested because we had a lot of users, which is very good thing for any code, public code. This is the 2009 schematics where we had, the first release of Python. You can see the API and procedural structures. We have Python layers, object layers, and C++ modules. This is in 2009 description. We have Sherpa help pages in Chao. This is the session UI, user interface layer. And we have Sherpa in Python documentation, which allows you to use Python API. Sherpa has been used in science. These are just different examples from last year. We have spectral modeling with NICER, Swift, Chandra. SDSS spectra has been modeled. Also examples of Sherpa and BXA, which you've heard presentation later, earlier in the week. And also the examples of 2D modeling of Chandra data, XMM data, and PSF fitting to improve astrometry in studying the movement of the point sources in the supernova remnants. So you can learn more. You can go to Sherpa webpage or GitHub webpage, and there are more detailed presentations during Channel workshops. You can see we have tutorials scheduled for September 1st at 10 a.m. And you can think about what you want to learn. We will have the question and answer session. You can also submit your questions via the form, which I will distribute over Slack channel or send to participants. We have a Google form with just a few questions where you can send them, hopefully by midweek next week, so we can address your questions during the tutorial on September 1st. Thank you. If you have questions, please ask.
Excellent. Thank you very much, Aneta. We have time for one question. I'm going to ask the question from Jeff Scargill, who asked, to what extent is Sherpa exclusively a spectral domain package? Are there also time domain tools?
So we don't have specific time domain tool in Sherpa at this moment. You can input light curve into Sherpa and you can fit with generic models. You can also design or define your model, and we have the user interface to build your own models outside. So you can have a model which you can input. In theory, there is no limitation on the data type and the model fitting, which you can do. We could try. Somehow there was no need for directly modeling time or light curves in Sherpa so far.
And in the spirit of bookending this talk with the coffee that we had this morning, I'm going to ask Vinay's question. What is the recommended citation for Sherpa?
Right, okay, so there are few, of course. This is the references. So the main citation is Freeman, Siemiginowska, 2001. This is the first citation, and this is the most cited one. The Python one is the Revsdal 2009, and then we have the code citation from Zenodo.doi, which points to the release and the most recent version of data, of the code. So if you use the Python one, then if you point to Zenodo.doi, you will point to the right version and the release version. So I would suggest all references.
All of them, yeah. Great. Thank you again, Aneta. Thank you all for a great session, and thank everybody for attending and for the questions that you have all asked during our session. I want to thank all of our speakers again. I also would like to remind you all that we meet next week. I will be sending a separate Zoom link for next week's sessions, and we start on Tuesday again.